I'm going to talk about our recent efforts towards whole body NPC for Nadia. And so I'd just like to frame the conversation by comparing template models, and I'll use the 3 potato model that we use a lot as an example against, say, the full rigid body dynamics. And we use the 3 potato model to capture the effect of Nadia's extremely heavy legs on angular momentum planning. So advantages of template models are they're easy to interpret and debug, they're quite robust and computationally efficient, but oftentimes you end up baking in some task-specific assumptions on your dynamics model, and that might result in a lack of expressiveness in a downstream controller. In contrast, your full rigid body dynamics are very expressive, and so in principle you should be able to toggle between different tasks by adjusting a cost function in a downstream optimization-based controller, and that means you're kind of using a more minimal set of task and robot assumptions. The disadvantages there, though, that it's extremely compute-intensive. In practice, you often need to do quite a bit of tuning and cost function shaping to get the behavior you want, and you can run into convergence issues. Oops. So to kind of front load the presentation a little bit, here's several maneuvers we've been working on Nadia. Top left is a walking gait, top right a running gait, and then we've got hopping forwards and hopping side to side on the bottom. And these are all the same general NPC formulation.
What are the 2 images?
Say again, sorry?
What are the 2 images? Ghost. What's the ghost in the dark?
So the dark is the actual state of the system. The ghost is the end prediction of the end time step of the NPC horizon, planning forward in time. And so we're building on a lot of great work from Justin Carpentier, the Pinocchio rigid body dynamics library. And more specifically, the Crocodile optimal control package from Carlos Mastali, who's joined IHMC on a part-time basis very recently. And so we're simulating the NPC in Bullet and streaming the results over to RViz for visualization. So for the problem formulation, Nadia's got 29 internal degrees of freedom, 6 DOF legs, 7 DOF arms, and a 3 DOF spine. We actually lock the wrist joints and the shoulder yaw joints because currently they contribute very little to the maneuvers we're trying to do. And so we end up with a state vector that's 55 dimensional, and our control vector is the joint torques, and that's 21 dimensional. So building on Carlos Mastali's work in Crocodile, we're solving with DDP. So we'll end up with a feed-forward torque command and a state feedback term, this gain matrix K. And in particular, we're building on this feasibility-driven work where we can warm start with infeasible state of control trajectories. So we're looking at the moment a horizon length of about 1 to 1.2 seconds. That's usually a step and a half in a walking gait or a little over a jump. Say if we're working on jumping, we find that if we use much less than a step, our results are quite meaningless. And so at the moment we're working towards 100 Hz solve rate on the NPC. That will likely come down when we move to hardware. We're probably benchmarking what kind of operator computer we need. But we are really interested in seeing if we can use this state feedback term, this K, in place of a whole body controller. And so at the moment we're using that at a 1 kHz rate in between NPC solves. And the user must supply footstep locations and timings, as well as swing height, so we can construct swing trajectories. We're kind of taking all the contact planning out of the problem at the moment. For control objectives, we've just got simple swing tracking and stance tracking tasks. Our constraints are enforced just with quadratic barriers at the moment, state bounds, control bounds, and wrench cone limits. The regularization terms are a lot more experimental. We're penalizing torso orientation, a tiny penalization on deviation from a stand-ready stance. And one thing we found underlined here in red is that we've actually got to supply a more informative reference for contact forces, specifically vertical contact forces. And so on the top right here, I've got the first dashed line is the robot's weight, the second dashed line is half the robot's weight. So essentially, we're supplying a vertical reaction force of the robot's weight divided by the number of active contacts. And you can see that's quite sharp and messy at the moment. We're looking at cleaning that up and making it more natural. So for observations, we've so far stuck to motions where warm starts from previous solutions and simple regularization work well. Parkour, which we're not necessarily interested in pursuing yet, but that probably won't fit into that category. NPC can be very difficult to tune, as I might have implied. It's a question of, are my cost weights poor, or do I need to add some reference information? Is my cost too sparse? And we do have some regressions from our current walking controller. We've got no push recovery or step adjustment heuristics for now. The contact wrenches can be difficult to specify in control, as I mentioned, and the computational expense will mean it's off board for the foreseeable future. So I've just got some points for moving forward. Of course, we need to move to hardware validation very soon. We're very interested in seeing how the state feedback game term fares on hardware instead of our whole body controller. My colleagues will talk later in the week about some of the template model controllers we're working on. It'll be really interesting to supply course references from them. And I am very interested in looking at adaptive approaches for updating the Dynamics model online. So thank you very much.
The user provides the contact location and timing.
Yes.
It's just hand scripted for now, or where does that come
For
from?
most of these maneuvers, yes. We're looking, so because we've been developing this in C++ and Python, it sits outside of our stack, which is the majority is in Java at the moment. We're currently upgrading the comps so we can use our step generators and planners.
And what enforces the timing?
So that information is used to make swing trajectories and their timing notes. Yes.
So I noticed your predictions and your actual closed loop match up really nicely.
Yes.
I would posit that the purpose of a prediction isn't to make accurate predictions of state space, but to make accurate predictions of your cost to go. Any comments on that? Yeah.
Say again. So it's to make accurate predictions of your cost to go?
Yeah, your terminal cost essentially.
Yes.
Repeat the question.
Me or?
So Steve's mentioned that the predictions of the NPC tend to match up with what the robot ends up doing really well. Steve said it's the purpose of NPC to give good estimation of your cost to go rather than the state you end up in. Is that fair?
Yeah.
I'm not sure I've thought too much about that personally. What are you trying to get?
We can talk more offline.
Yeah, I'm interested in what you're getting there. But
When we look at our predictions, they're often very off,
yeah,
but they estimate the cost to go very well, and so your closed loop is actually pretty good.
yeah. I wonder how kind of like model mismatch factors.
We're using reduced order models, but
Yeah.
we can talk about it more.
Yeah.
So the U matrix, is that velocities or accelerations?
The U vector,
Yeah, the input vector.
that's joint torques.
Joint torques?
Yes.
Wow. That's expensive.
What's the physical bandwidth of the robot? Or different parts of the robot?
Off the top of my head, not too sure, but to kind of get at what you might be implying, I think that we're going to run into, using kind of these state feedback gains, assuming a perfect model, I think it's likely that when we transfer to hardware, we run into some issues where these gains are really quite stiff, and we have to make some changes to our algorithm. What extensions we make, I don't know, but I think we'll run into some trouble there if I had to. Yes.
I don't think that was my question, actually. I was
sorry.
going to ask a philosophical question, which is, it's probably not 100 hertz or 50 hertz. So why do you need 100 hertz MPC for it? Why is that a good idea?
Yeah, I'm not necessarily sure that's like a hard deadline we must reach. It's just that, you know, when you start getting quite low in these solid frequencies, the performance, at least as we observe, tends to degrade. That's just a ballpark rule, no doubt.
latency.